Welcome to AI, tokenization, and more. This is your Professor Atif Fareed Muhammad. In this discussion, we'll look into tokenization, stemming, lemmatization, text representation, and raw text to machine ready data in quite depth. Text processing is a foundational step in natural language processing that converts unstructured raw text, such as documents, social media posts, or customer reviews, into structured, machine-readable data for analysis. This process involves a series of techniques including tokenization, split text into words or sentences, part-of-speech tagging, named entity recognition, and syntactic parsing, which collectively extract meaningful patterns and relationships from the text. Advanced methods like topic modeling, sentiment analysis, and word embedding, such as word2vec or BERT, further refine this data, enabling applications such as automated summarization, chatbots, and predictive analytics. By transforming raw text into structured formats, text processing unlocks the potential of data-driven insights, enhancing decision-making in fields like marketing, healthcare, and customer service. Now let's look into the text processing enabling machines to understand, interpret, and derive insights from human language with a use case. Text processing is the backbone of natural language understanding, empowering machines to parse, analyze, and extract meaningful information from human language. By applying techniques such as tokenization, syntactic parsing, and semantic analysis, raw text, whether from documents, social media, or conversations, is transformed into structured data that algorithms can interpret. Advanced methods like sentiment analysis, entity recognition, and deep learning based embeddings further enable machines to grasp context, detect nuances, and uncover actionable insights. This capability is foundational for applications like chatbots, recommendation systems, and predictive analytics, ultimately bridging the gap between human communication and machine intelligence. So now we'll go in the next slides and discuss the key steps include tokenization, normalization, and vectorization in more depth. So why processes text? Why pre-process the text? Now this is a great question. Let's jump into this with a real-time example. Imagine a customer service chatbot for an e-commerce platform like Amazon. Every second, thousands of customers type queries such as, "I want to return my order number 12345. It is damaged. How do I track my package?" Or, "This product is not what I expected." Without pre-processing, the chatbot would struggle to understand these inputs due to variations in spelling, punctuation, slang, or irrelevant details like order numbers or emoticons. Pre-processing, such as converting text to lowercase, removing punctuation, and filtering out stop words like I, my, or is, standardizes the input, permitting the chatbot to focus on the core intent: return order, track package, product complaint. In real-time scenario that we are discussing, pre-processing also involves tokenization, splitting sentences into words or phrases, and lemmatization, reducing words into their base forms, like turning damaged into damage. For example, the phrase "I am really unhappy with my purchase" becomes "unhappy purchase." After pre-processing, this simplification helps the chatbot's natural language processing model classify the sentiment as negative and route the query to the correct department, whether it's returns, refunds, or customer support without being misled by emotional language or informal expressions. The text pre-processing ensures that chatbot can handle noise in real-time conversations such as typos, RETUN instead of return, RETURN, abbreviations such as PLS or please, or multilingual inputs. Das ist nicht gut, which in English translates this is not good. Techniques like spell checking, language detection, and entity recognition, identifying order numbers or product names, further refine the input. Without these steps, the chatbot might misinterpret requests, leading to frustrated customers and inefficient service. In high stakes environment like e-commerce, pre-processing is not just a technical step. It is difference between a seamless customer experience and operational breakdown. So let's jump into tokenization, which is an area in itself of extreme intellect, interest, and intrigue for the actual natural language processing, natural language understanding, and natural language generation. What is tokenization? So let's take a social media example like Facebook, or you can say a workbook, or Instagram, or TikTok. And in specific Facebook, because it has tons of text, every post, comment, or message you see is processed by algorithms to understand content, detect spam, or personalize your feed. Tokenization is the first critical step in this process, where raw text is broken down into smaller, meaningful units called tokens. For example, if you post just had an amazing dinner at Central Park Cafe, and then you put foodie there as the hashtag. For example, when we type any of such thing, we just saw a movie, and you say moviegoer as a hashtag. Tokenization splits the sentence, the first sentence I mentioned, into individual components. Just had an amazing dinner at Central Park Cafe, and sign of exclamation. So I have deliberately given a pause after every word. And then last not least comes foodie, the hashtag. These tokens can be words, punctuations, emojis, or hashtags, each serving as a building block for further analysis by Facebook's AI system. Tokenization helps Facebook's algorithm categorize and analyze content efficiently. For instance, the token foodie might trigger the system to associate your post with food-related communities or ads, while Central Park Cafe could be recognized as a location or business page. And even if you have entered an emoji, is still tokenized to infer the context. So this all refines content recommendations or targeted advertisements. Without tokenization, Facebook's AI would struggle to distinguish between the different elements of your post, making it nearly impossible to deliver relevant content or moderate harmful material. Beyond content analysis, tokenization is essential for real-time features like autocorrect, language translation, and sentiment analysis. When you type a comment, Facebook's system tokenizes each word as you go, enabling it to suggest corrections. So if you say AMZING, which should be amazing, AMAZING, or translate your text into another language, it also helps detect hate speech or misinformation by isolating specific words or phrases. Tokens like scam or fake that may flag a post for review. In essence, tokenization is the invisible foundation that allows Facebook to process billions of interactions daily, turning unstructured data into actionable data for everything from personalization to safety. This is applicable on LinkedIn as well. So the word tokenization breaks text into individual words, as mentioned earlier, based on white space and punctuation. That's where I gave the pauses. Challenges include handling contractions, hyphenated words, and language specific rules. So I am learning NLP. So I am is technically 1, learning is 2, and NLP is 3. Sentence tokenization. Sentence tokenization splits text into sentences, respecting punctuation and abbreviations. Important for tasks like sentiment analysis and machine translation. Hello, how are you? Goes hello as one token, and how are you would become the second token. Subword tokenization. Subword tokenization split words into smaller units such as unhappiness. Un becomes 1, happiness becomes second. Useful for handling rare words and morphological variations. Popular in models like Bird and Word Peace. So let's take LinkedIn as our next social media. This is where users post professional updates, job descriptions, and industry-specific jargons. Like subword tokenization plays a crucial role in helping the platform's AI systems understand and process language effectively. Unlike traditional tokenization, which splits text into whole words, as mentioned earlier, subword tokenization breaks words into smaller, as also mentioned earlier, in reusable units, such as machine and learning from machine learning, or data and sci from data science. This approach is particularly valuable on LinkedIn, where technical terms, acronyms like AI, CEO, SaaS, and hybrid words like blockchain, neurodiversity are common. By decomposing words into subword units, LinkedIn's algorithms can better handle rare or complex terms, improving tasks like job matching, skill recommendations, and search accuracy. Subword tokenization also enables LinkedIn to support multilingual and specialized content seamlessly. For example, a user's profile might include terms like das ist gut or künstliche intelligence. So künstliche intelligence in German is artificial intelligence, and das ist gut, this is good. So these are some of the examples. Instead of treating these unknown words, subword models break them into familiar subunits. So Kunst, Kunst, is in German. Lische is the next subword. Intelligence is the next subword, and that is the artificial intelligence. Permitting the system to infer meaning even when encountering new combinations. This flexibility is essential for global platforms like LinkedIn, where users interact in diverse languages and industries. By leveraging subword tokenization, LinkedIn ensures that its AI tools, from resume parsing to content moderation, remain robust, inclusive, and adaptable to evolving professional lexicon. The popular models like Bird and WordPeace are some of the examples. Character tokenization. It breaks text into individual characters, helps with languages without spaces or spellings. Spelling correction, cat like CAT, cat is on the mat, MAT, and ON are separate. Cat is on the mat. Every single letter would be tokenized. Now let's look into some challenges in tokenization in a little more depth. Tokenization, while foundational to natural language processing, is far from straightforward due to the inherent complexity and ambiguity of human language. One of the primary challenges is handling ambiguous or context-dependent words. For example, the word like can function as a verb, I like coffee, a preposition, she acts like a manager, or even as slang, the post got like 100 likes. Tokenization must accurately identify the role of each word to avoid misinterpretation, which can lead to errors in downstream tasks such as sentiment analysis or machine translation. Similarly, contractions don't for do not and possessives John's or John is or John has. Another significant challenge is dealing with out of vocabulary words, OOV, which are terms that a tokenizer has not encountered during training. This issue is particularly prevalent in domains like social media, where slang, misspellings, and creative word formations like adorable, hungry are common. In professional or technical contexts, such as LinkedIn or scientific literature, specialized jargons or newly coined terms like metaverse, quantum supremacy, can also stump traditional tokenizers. Subword tokenization techniques like byte pair encoding or BPE or word piece, as mentioned earlier, these are significant add-ons. So these all significant add-ons help mitigate this by breaking words like smaller known subunits, but they are not foolproof. OOV or out of vocabulary words can still lead to misclassification or loss of nuance, impacting the performance of applications like chatbots, search engines, or recommendation systems. Multilingual and cross-lingual tokenization presents a unique set of challenges. Languages vary significantly in structure, grammar, and writing systems, making it difficult to create a one-size-fits-all tokenizer. For instance, languages like Chinese and Japanese do not use spaces to separate words, requiring specialized segmentation techniques. Meanwhile, these languages like Finnish or Turkish form long, complex words by combining morphemes, which can overwhelm tokenizers that rely on fixed vocabularies. Additionally, code switching, the practice of alternating between languages in a single sentence, adds another layer of complexity. These challenges highlight the need for adaptive, language-aware tokenization strategies that can accommodate the rich diversity of human communication without sacrificing accuracy or efficiency. Normalization techniques. We like to normalize things. When we look at a robot and it does not have a face, it's not a normalized thing as a human. But as soon as the robot gets a human face, it starts becoming more familiar or familial understanding. Stemming. Let's jump into this with a real-time example. Now, here is a good question that we can ask. Why stemming, or why stemming is important? Stemming is a critical text pre-processing technique that reduces words to their root or base form, helping systems recognize that variations of a word such as running, ran, and runner all stem from same core concept, run. This process is especially valuable in customer support chatbots, where users express the same issue in countless ways. For example, a customer might ask, "Why is my order delayed? My package has not arrived yet," or when will my shipment be delivered? Without stemming, a chatbot might treat delayed, has not arrived, and shipment as entirely unrelated terms, leading to fragmented or irrelevant responses. By stemming these words to their tools, delay, arrive, and ship, the chatbot can group similar queries together, improving its ability to understand intent and provide accurate, consistent answers. Consider an e commerce platform like Amazon or Alibaba or something else, Walmart, where thousands of customers' inquiries flood in daily. A user might type, "I'm having trouble tracking my order," while another writes, "Tracking is not working for my purchase." Stemming performs a transformation like tracking and track into the same root, track, permitting the chatbot to recognize that both users and are experiencing the same issue. This is not only streamline the processing of routing queries to the appropriate support team, but also enables the system to analyze trends, such as a spike in tracking related complaints, more effectively. Without stemming, the chatbot might fail to connect these queries, leading to slower response times, redundant efforts, and a poorer customer experience. Beyond improving accuracy, stemming also enhances efficiency in data storage and retrieval. In large scale systems, storing every variation of the word, like connecting, connected, connection, would require significantly more memory and computational power. By reducing words to their stems, databases can be optimized and search algorithms can operate faster. For instance, when a customer searches for return policy in a help center, stemming ensures that reserves for returning, returns, and return are all included, making the search process more comprehensive and user friendly. In this way, stemming not only refines the performance of AI driven systems, but also contributes to a smoother, more intuitive interaction between users and technology. Now let's look into, in the same way, why lemmatization. Lemmatization is a sophisticated text normalization technique that reduces words to their base or dictionary form, known as the lemma, while ensuring the result remains a valid and meaningful word. For example, it transforms words like signing to sign, amended to amend, and was to be. This precision is crucial in legal document analysis, where the exact meaning of terms can significantly influence interpretations and legal outcomes. In a contract, phrases like "the agreement shall amend," "the agreement is amending," and "the agreement has amended" all center around the same core action. Amend lemmatization ensures that variations are standardized, enabling legal AI tools to accurately identifying obligations, rights, and conditions without losing context. Imagine a law firm using AI driven software to analyze thousands of contracts for compliance or risk assessment. Without lemmatization, the system might treat breach, breached, and breaching as unrelated terms, potentially missing critical clauses tied to contract violations. By lemmatizing these words to their base from breach, the software can detect patterns and inconsistencies, such as conflicting breach conditions across multiple documents. This capability is vital for tasks like due diligence, where overlooking a single variation as a term could lead to legal oversights or disputes. Lemmatization ensures the AI understands the nuances of legal language, enhancing both accuracy and reliability in high stakes situations. Beyond improving comprehension, lemmatization also enables cross document comparisons and efficient knowledge extraction. For example, when reviewing a case law, legal professionals often need to find precedents where similar arguments or rulings were applied. Lemmatization also asserts tools to recognize that appealing, and appeal all relate to the lemma appeal, ensuring comprehensive retrieval of relevant cases. This not only saves time but also minimizes the risk of human error in manual reviews. In fields like law, where precision and context are critical, lemmatization transforms raw text into actionable insights, empowering AI systems to serve as effective partner in legal analysis and decision making. So better, good, running, run. So better transforms to good, running transforms to run. Now let's look at the subtle differences between stemming and lemmatization with few examples. Let's look at few significant words that we use in our everyday life. Better and good. One of the key differences between stemming and lemmatization is evident in how they handle irregular words. For example, the word better is derived from the adjective good. Stemming algorithm, which rely on crude heuristics like chopping off suffix and often fail to reduce better to its root and may leave it untouched or incorrectly transform into something like better, the same thing. In contrast, lemmatization uses vocabulary and morphological analysis to correctly identify that lemmas of better is good. This distinction is crucial in applications like sentiment analysis, where understanding the true meaning of comparative words can significantly impact the accuracy of the analysis. Another is was and be. Another example that highlights the differences is the treatment of verbs in different tenses. Take the word was, which is past tense of be. A stemming algorithm might strip away the suffix or leave it as is, resulting in an output like wa for was, neither of which is meaningful root. Lemmatization, on other hand, recognizes that was is a form of a verb be, that be, and correctly reduces it to its lemma. This capability is particularly important in applications like chatbots or virtual assistants, where understanding the correct form of verbs is essential for generating coherent and contextually appropriate responses. Another could be caring and care. The word caring produces or provides another illustrative example. Stemming algorithm often apply a simple rule to remove the suffix ing, resulting in a stem of car, which is car, not care. While this might be useful in some contexts, it loses the actual meaning of the word, which is related to care, care, not car, which is an automotive or a vehicle. Lemmatization, however, correctly identifies the lemma as care. This precision is vital in fields like healthcare and customer service, where the nuanced meaning of words can influence the interpretation of patient feedback or customer reviews. For instance, understanding that caring relates to care helps in accurately categorizing sentiments and concerns. This mice and mouse is another example. The difference between stemming and lemmatization is also apparent in the handling of irregular plurals. Consider the word mice, which is plural form of mouse. Stemming algorithm which do not account for irregular forms, might incorrectly process mice as MIC, not MICE, or leave it unchanged. Lemmatization, however, recognizes the relationship between mice and its singular form mouse and correctly reduces it to the lemma. This accuracy is particularly important in applications like information retrieval or text classification, where correctly identifying the base form of words can improve the relevance and precision of search results or categorization. Now let's look into text representation in a little bit more depth. Bag of words, or BOW. The bag of words model is a simple yet powerful technique in natural language processing that represents text as a collection of words, disregarding grammar and words or word order, but preserving frequency. In this approach, a document is converted into a bag or multi-set of its words, where each word is treated as an independent feature. For example, the sentence "the cat sat on the mat" could be transformed into a set like "the." It came in twice because the cat sat on the mat. Cat came in once, sat came in once, on came in once, and mat came in once, where the numbers indicate how often each word appears. While bag of words or BOW ignores context and sequence, it provides a straightforward way to quantify and compare textual data, making it a foundational tool for tasks like document classification, sentiment analysis, and information retrieval. And why should we care about the bag of words? That's a great question comes to my mind. Bag of words is essential because it serves as the backbone for many NLP applications, particularly in scenarios where simplicity and efficiency are prioritized. For instance, in spam detection, bag of words help classify emails by analyzing the frequency of words like free, win, or urgent, which are often associated with spam. Similarly, in search engines, bag of words enable quick matching of user queries to relevant documents by comparing word frequencies. Its computational efficiency and ease of implementation make it go-to method for pre-processing text before applying more complex models, such as machine learning algorithms or neural networks. Without bag of words, many early NLP systems would struggle to handle large volumes of text data effectively. Limitations and evolution of bag of words are another area that we can ponder upon. While bag of words or BOW is widely used, it has notable limitations such as its inability to capture semantics, word order, or context. For example, the sentence "the dog bit the man" and "the man bit the dog" would be represented identically in bag of word model despite their vastly different meanings. To address these shortcomings, advanced techniques like TF-IDF, term frequency inverse document frequency, word embeddings, word2vec or glove, and transformer-based models like BERT have been developed. However, bag of word remains relevant as a baseline or preliminary step as in many NLP pipelines, especially when working with limited computational resources or large-scale datasets. Its simplicity and interpretability continues to make it a valuable tool in NLP toolkit. The count vectorization. Now let's look into this with an example. Count vectorization is a technique in natural language processing that converts a collection of text documents into a numerical matrix by counting the frequency of each word in the corpus. Unlike the bag of words model, which represents individual documents as word frequency dictionaries, count vectorization creates a structured matrix where each row corresponds to a document. Each column represents a unique word from the entire corpus, and the values indicate how often each each word appears in a given document. For example, if we have the two sentences, the cat sat on the mat and the dog played on the mat, count factorization would generate the matrix with rows for each sentence and columns for words like the cat, sat, etc., with counts reflecting their occurrences. This method transforms unstructured text into a format that machine learning algorithms can process, enabling tasks like classification, clustering, or recommendation systems. Count factorization is a fundamental tool in natural language processing because it bridges the gap between raw text and machine learning models, making it possible to apply statistical and algorithmic techniques to textual data. For instance, in sentiment analysis, count factorization helps quantify the presence of positive or negative words in customer reviews, permitting models to predict overall sentiment. Similarly, in document classification, it enables systems to categorize news articles, emails, or social media posts based on word frequency patterns. Its simplicity and effectiveness make it a popular choice for pre-processing text in applications where interpretability and computational efficiency are important. Count factorization serves as a stepping stone for more advanced techniques like TF-IDF as well, the term frequency inverse document frequency, which further refines word importance by considering rarity across documents. While count factorization is powerful, it shares some limitations with the bag of words model, such as ignoring word order, context, and semantics. For example, it would treat I love this product and I hate this product in similar fashion if they contain the same words despite their opposite meanings. To overcome these challenges, modern NLP often combines count factorization with techniques like n-grams, which capture word sequence, or embeddings, which encode semantic meaning. Count factorization remains a cornerstone in text preprocessing due to its speed, scalability, and ease of use. It is frequently used as a baseline or initial feature extracting step in pipelines, particularly when working with large datasets or resource-constrained environments. Its role in NLP continues to evolve as part of hybrid approaches that integrate both traditional and cutting-edge methods. So since we are discussing on TF-IDF, let's look into this with a real example. So the TF-IDF, as mentioned earlier, the term frequency inverse document frequency is a statistical technique used in natural language processing to evaluate the importance of a word in a document relative to a collection of documents known as a corpus. It combines two key metrics, term frequency, which is TF, while measures how often a word appears in a specific document, and inverse document frequency, or IDF, which assesses how rare or common a word is across the entire corpus. For example, in the document about machine learning, the word learning might appear frequently high term frequency, or TF. But if it also appears in many other documents, its IDF, or inverse document frequency, would be low, reducing its overall TF-IDF score. Conversely, a specialized term like neural networks might have a lower term frequency but a high inverse document frequency if it appears in fewer documents, signaling its importance. The TF-IDF transforms text into numerical matrix where each word's significance is weighted, making it easier for algorithms to identify meaningful patterns. TF-IDF is a cornerstone in NLP because it addresses a critical limitation of similar and simpler methods like bag of words or count factorization. Not all words are equally important. For instance, in search engine, TF-IDF helps prioritize documents that contain rare relevant terms over those filled with common but less meaningful words like the and is. In text classification, it enables models to distinguish between documents based on the uniqueness of their vocabulary, improving accuracy in tasks like topic modeling, spam detection, and sentiment analysis. TF-IDF is also computationally efficient and interpretable, making it a go-to choice for applications where understanding the why behind a model's decision is as important as the decision itself. Its ability to highlight contextually significant words makes it indispensable in information retrieval and data mining. While TF-IDF is highly effective, it has limitations. It still ignores word order, context, and semantics, meaning it cannot differentiate between I love this product and I hate this product if they share the same TF-IDF weighted words. Additionally, it struggles with polysemy, words with multiple meanings, and synonymy, different words with similar meanings. Despite these challenges, TF-IDF remains widely used, often as a pre-processing step before applying more advanced techniques like word embeddings like word-to-vec, glove, or transformer model. In modern NLP pipelines, TF-IDF is frequently combined with other methods to enhance performance, such as using it to initialize embeddings or as a feature in hybrid models. Its simplicity, scalability, and effectiveness ensure its continued relevance in both research and industry applications. So NLP in a tech document gets a higher score than a general corpus is another example. N-grams. This is a very, very nice thing that we should learn together. And let me give you a few examples on n-grams. N-grams are contiguous sequence of n items, typically words or characters, extracted from a given text. In NLP, n-grams capture local context and word order, addressing a key limitation of bag of words and count vectorization, which treat words in isolation. For example, in a sentence, I love natural language processing, a bigram or 2-gram model would generate pairs like I love, and then love natural, and then natural language. And last not the least, language processing. Similarly, a trigram or 3-gram would produce sequences like I love natural language, and so on. By preserving word sequences, n-grams help models understand phrases, idioms, and contextual relationships, such as distinguishing not good, negative from good, positive, in sentiment analysis. This makes n-grams a versatile tool for tasks like text classification, machine translation, and speech recognition. N-grams are essential because they bridge the gap between simple word frequency models and more complex semantic techniques. For instance, in spam detection, a bigram free money might be a stronger indicator of spam than individual words free or money alone. In autocomplete and search engines, n-gram improve predictions by considering the likelihood of word sequence struggling New York after the word the user types new. They also play a critical role in language modeling. Before, the probability of a word depends on the words that precede it, enabling applications like predictive text and voice assistants. While n-gram requires more computational resources than bag of words, their ability to capture context makes them indispensable for improving the accuracy and nuance of NLP systems. Despite their advantages, n-grams have notable limitations. The most significant is the curse of dimensionality. As n increases, the number of possible n-grams grow exponentially, leading to separate and sparse data and higher memory usage. For example, trigram model for a large corpus might generate millions of unique sequences, many of which appear only once. This sparsity can degrade performance in machine learning models. Additionally, n-gram struggles with long-range dependencies, connecting words separated by several clauses and out-of-vocabulary phrases in dynamic or creative language, use slang or neologism. To mitigate these issues, modern NLP often combines n-grams with techniques like smoothing, Laplace or Cart's backoff, or embedding word-to-vec or BERT, which represent words in dense vector space. Today, n-grams remain a staple in hybrid models where they complement the deep learning approaches by providing interpretable local context in tasks like named entity recognition, text generation, and information retrieval. Word embeddings. So represents word as dense vectors in a continuous space, captures semantic relationships such as king, man, woman, queen. And I don't think any other example fits here. Either it's a king or a queen ruling a country. And in the democratic societies, we have replaced that with president or prime minister. It can be both. So word-to-vec and glove are the few examples associated with this. Character level representations uses tensors to represent characters, useful for spelling corrections and rare words, captures morphology and subword information. Hello tensor is HELLO, and that's how we use tensor. Tensor representations, tensor generalize matrices to higher dimensions of characters, words, or sentences. Enable efficient processing in deep learning models. 3D tensor for a batch of sentences, batch size, sequence length, and embedding dimension is also significantly important. One-hot encoding. Now let's look into this with a little bit more detail. One-hot encoding is a technique used in natural language processing and machine learning to convert categorical data, such as words in a text, into a binary vector format that machines can process. In this method, each word is a vocabulary assigned in a unique index, and every document or sentence is represented as a vector where each element corresponds to a word in the vocabulary. If a word appears in the document, its corresponding position in the vector is set to 1, while all other positions are set to 0. For example, if your vocabulary is cat, dog, bird, and your sentence is the cat sat, the one-hot encoded vector for cat would be 1, 0, 0. This approach transforms text into a structured numerical format, making it compatible with algorithms that require numerical input, such as neural networks or traditional machine learning models. One-hot encoding is important because it provides simple, intuitive, and effective way to represent textual data for computational processing. In applications like text classification, it allows models to distinguish between different words by treating each as a distinct feature. For example, in a sentiment analysis task, one-hot encoding can help a model recognize that the presence of words like happy or sad correlates with positive or negative sentiments, respectively. It is also widely used in recommendation systems where user preferences or item descriptions are encoded to match similar items or predict user behavior. While one hot encoding does not capture semantic relationships or word order, its simplicity and ease of implementation make it foundational step in many NLP pipelines, especially when working with smaller datasets or simpler models. Despite its utility, one hot encoding has significant limitations. The most pressing is dimensionality. As the vocabulary size grows, the vector becomes extremely sparse, mostly filled with zeros, which can lead to inefficiencies in storage and computation. For example, encoding a document with 10,000 unique words would result in 10,000 dimensional vector with mostly zeros, making it impractical for large scale applications. One hot encoding fails to capture semantic relationships between the words like king and queen, are treated as entirely unrelated even though they have or they share similar meanings. To address these issues, modern natural language processing often replaces one hot encoding with dense embeddings, and those are word-to-vec, glove, or bird, while represent words as low-dimensional vectors that encode semantic and contextual information. However, one-hot encoding remains relevant in specific scenarios such as pre-processing or traditional machine learning models, or when interpretability is more important than capturing complex relationships. Practical applications. Tokenization and TF-IDF improve search relevance and speed, and these are the applications in search engines. Stemming lemmatization helps match user queries to documents. Searching running retrieves documents with run or ran. Applications in chatbots or voice bots or agents. Tokenization and embeddings enable understanding user input. Lemmatization normalizes user queries for better intent recognition. I am running late. Intent is delay. The key takeaways: tokenization and normalization prepare text for analysis. Vectorization, the bag of words, term frequency, inverse document frequency embeddings, converts text to numerical form. Choose technical based or techniques based on task, language, and computational constraints. Then that is your call which one you go and pick. Happy learning. See you in next lecture.